Hi everyone, so I'll be doing a first course in abstract algebra. So, what is interesting about algebra is that we like to understand structures and vary those structures with respect to each other and see how they sit with respect to each other, and from that we get information encoded as mathematics. So I'll be following Thomas Hungerford. So the very starting point of the book starts out with the integers, which is z, and that set is, the elements of that set is 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. And how that looks like if we graph it, it would just look like a lattice. So it would just look like a bunch of points everywhere in the graph here that are spread evenly apart from each other, but there are gaps in between them. So you guys get the picture. So for instance, this point in red here is the point 1, 1, etc. So what's interesting about the integers is that any subset of non-negative integers will contain a smallest element just because of the fact that the integers are, the main fact is for this, conceptually speaking, is that all the integers are either increments of 1 or decrements of 1. So from this idea, if we bring a set of non-negative integers, we can keep moving to the left by 1 until we find an element in the set of non-negative integers, which is the smallest element with respect to that set. So let's encode that axiom and write it down. So, well, ordering axiom. So a lot of the things that we expect with numbers, with the integers, they happen really because of the well-ordering axiom. So every non-empty subset of the set of non-negative integer contains a smallest element. So just as an example, if we see the even numbers, excluding the negative even numbers, so 0 to 4 and 6, etc., we can see that we have that 0 is a minimum element. And what's interesting about this is that the main idea really rests on the fact that the integers like they also don't have the property that if you keep decreasing by certain amount, you find that there is a lot of elements between two integers. That's also one of the main reasons for why we have also why the integers are expected to have why we enforce that axiom. So let's remember the grade school division. So remember, if we want to divide 7 by 82, we ask ourselves how many 7s go into 82. So it's 11 times. So then 11 times 7 is 77. And we get a remainder of 5 because 7 doesn't go into 5. So as you can see here, 82 is 7 multiplied by 11 plus 5. So we expect that the remainder would be less than 7 because if it was bigger than 7, we would have a number where we multiply the 7 by an extra amount, and we get plus a certain amount which is less than 7, because we can decompose that number which is bigger than 7 into something less than 7 and bunch of 7s, and we will end up with 7 multiplied by a number plus something less than 7. So that's the main core reason. So let's see a couple of language. So here 82 is called the dividend. And we have that is equal to the divisor, which is 7. We're dividing 82 by 7. And that is multiplied by a quotient, which is the 11 in this case. And we have a remainder. We have the following theorem, which encodes this grade school division, and it encodes it in a language that we can use for other things. So we have the following theorem. Theorem 1.1, the division algorithm. So what the division algorithm say is that given two integers, you can always divide one of the integer by another integer to get a quotient as well as a corresponding remainder, where that remainder is less than the divisor. So let's write that down. Let A and B be integers with b greater than 0, then there exists unique integers Q and R such that A is equal to B times Q plus R, where R is bigger than 0 and less than B. So the main idea of the proof is that we can keep subtracting multiples of b until we arrive at a number which is as minimum as possible. And we are guaranteed to find the number which is minimum as possible by the well-ordering axiom. So let's prove the result. So let a and b be fixed integers with b bigger than 0. Consider the set S, where the set is M belonging to Z, where M is of the form A minus BX which is bigger than 0 for M belonging to the integers. Sorry, for X belonging to the integers. So first of all, we would like to invoke the well-ordering axiom. So first step is that we have to show that in order to invoke it, we have to show it is non-empty. Well, we are guaranteed that it is a non-negative. So, and we will show that it is non-empty, then we can find a minimum element by the well-ordering axiom. So, consider X being equal to minus the absolute value of A. Then what I have here is that I say that A minus B multiplied by minus the absolute value of A, that is bigger than or equal to 0. Well, let's show that. First of all, since B is bigger than 0, B is bigger or equal to 1. So that means if you multiply A, the absolute value of A, by that, you have B times the absolute value of A, that is bigger than the absolute value of A, which is bigger or equal to minus A. So that means if you do algebra, that A plus B times the absolute value of A is bigger or equal to 0. So we have that A minus B times the negative absolute value of A, which is A plus B times the absolute value of A, is bigger or equal to 0. So we're guaranteed that this set S is non-empty. So therefore, S is not empty. So by the well-ordering axiom, we have that S has a minimal element. I'm going to call it R. So we have, since R by definition is A minus Bx, which is bigger than 0. So R is bigger than 0. And we call that particular integer, x belonging to z, we denote it by q. So we have that R is equal to A minus B times Q, where R is bigger than or equal to 0, or more equivalently, A is equal to B times Q plus R, and R is bigger than or equal to 0. So we have constructed R. So what we would like to show is that first, that this R is less than B. And the second thing that we want to show is that those R and Q that we constructed are unique. So to show that R is less than B, not Q, less than B, we use the well-ordering axiom. So the main idea really rests on what I have said before, is that you can, let's say you get that R is bigger than B, then you can get a higher quotient and something which is less than B. So that is encoded by the well-ordering axiom. So suppose by a contradiction we have that R is bigger than B, then that means that R minus B is bigger than 0. So we have 0 is less than R minus B. So we have that R is A minus B times Q minus B. So that's equal to A minus B times Q plus 1. So we have by definition that R minus B is positive, because that's what by assumption from the fact that R is bigger than or equal to B. So then that means that R minus B, as it is of the form A minus Bx, is an element of S. So R minus B, which is A minus B times Q plus 1, is an element of S. And by construction, we have that R minus B is less than R, which is an element of S, and by construction we have R is the smallest such element of S. So that means that R minus B is smaller than R, and it is also an element of S, so that's impossible. So that gives us a contradiction. So that means the contradiction was achieved from the fact that R is bigger or equal to B. So we must conclude that R is less than B. So therefore, we found integers Q and R such that A is B times Q plus R, and R here is less than B and bigger than 0. So the final step that we will do is that show that this R and Q are unique. So we show R and Q are unique So suppose we can write it in two different ways. So suppose A is equal to another B times another quotient plus another remainder, where is guaranteed that this remainder is less than B, and we want to show that Q1 is equal to Q and R is equal to R1. So what we have is B times Q plus R is equal to B times Q1 plus R1. So then that means by algebra we have B Q minus Q1 is equal to R1 minus R. So here we have that 0 is less than or equal to R, is less than B, and we also have 0 is less than or equal to R1 is less than B. So that means that if we multiply R by -1, we have minus R is less than or equal to 0, and it is bigger than minus B. So if we add that to R, the inequality of R, then we find out that the inequality of R1, we add it to the inequality of R1, then we find out that R1 minus R is less than B, and it is less than minus B, and here, so sorry, that R1 minus R. So then that means that we have that R1 minus R is an integer that is between minus B and B. So let's see what we can conclude from that. So we know that we have B times Q minus Q1 is equal to R1 minus R. So therefore, we have that B times Q minus Q1, this is between B and negative B. So therefore, Q minus Q1 is between 1 and negative 1. And Q minus Q1 are integers that are between negative 1 and 1. So that means that Q minus Q1 is 0. So therefore, so therefore we can conclude that R1 minus R is 0 as well. And we find that Q is equal to Q1 and R is equal to R1, and so we get uniqueness. So as I've explained, the main idea rests on the fact that there is that we can always go to the left of Z by decrementing by 1. So the well-ordering axiom is very useful in regards to the proof that we've established here. So thank you so much, and I will see you in future videos where I will be problem solving. I'll go through all of the book and problem solving all the problems as well. Thank you so much. See you.